Eh? Okay, so far we've done areas and we've done volumes. Now we're going to get lengths. We're going to get lengths of curves. You're going to deal with this situation where you're going to, have a graph like this, and someone's going to say, what's the length of this curve? That is, if you were a car driving, what distance would your odometer read? Or if this were on a piece of paper, what length of string would you need to put on this guy to get the exact length of that thing? And they call it arc length. You're used to an arc being, like a length of a curvy part of a circle, but actually in this case, arc length just means the length of this, curvy line. Find the length of that curvy line. And with areas, what you added up were a bunch of rectangles, and with volumes, what you added up were either a bunch of square wafers or triangular wafers or circular wafers or washers, okay? Here, in arc length land, you'll be adding up a bunch of hypotenuses. You're gonna get a bunch of hypotenuses. So so pretty soon you're gonna get a formula for getting arc length, and then you can mindlessly plug into the formula. So what I'm going to do is derive the arc length formula and then give you a couple practice problems where you get to mindlessly plug into the arc length formula. And then finally we'll do part C, which asks the question, what if f prime is undefined on the bounds of your arc? Then you don't get to use the arc length formula. Well, the answer is, yeah, you still get to use it. You're just going to have to go to dy land instead of dx land. And that's the last thing. But let's go ahead and derive the formula for arc length. Okay, so do I want to use this drawing? Oh, no, I think I'll do it, a bigger drawing. Here we go. First, deriving the formula for arc length that you will soon be mindlessly plugging into. Okay, so imagine you had, let me see if I can get a red or black pen. Imagine you've got some graph that looks like this, and you want to know what the length of this curvy line is. Okay? Well, you want to find the length from A to B. Alrighty? Well, the way you're going to get that length is you're going to divide this region between A and B into a bunch of partitions, just like we did with rectangles. So divide it into a bunch of partitions, and you can get this guy here, and get this point, and get that point, and get that point, and get that point, and get that point, okay? But instead of getting areas of rectangles, you are going to just connect the dots with straight lines. You got this straight line, you got this straight line, you got that straight line, that line, that line. You see that? You're just going to connect the dots with straight lines and get the lengths of those straight lines and say, okay, well, that's close enough, So these partitions don't have to be equally spaced. I didn't make them equally spaced, although they kind of look a little equally spaced. Maybe I should have exaggerated it more. But let's say this first distance is delta x1 from there to there, and this next distance is delta x2, and this next partition width is delta x3, and so on, okay? And so each partition, here I'll go below it. Looking at this first blue line, I can see that that blue line is the hypotenuse of a right triangle. A hypotenuse of a right triangle where one leg is delta x1 and the other leg is delta y1. And you know what, I have to tell you right now, you don't have to write this down. It's enough just to watch and enjoy. I see you guys writing it down and I appreciate it, but it's okay that you just watch and enjoy, because the big thing is, one of the ways you're going to be able to memorize the Arclength formula is to remember that it comes from Pythagorean theorem, to remember that it comes from the fact that you're finding a bunch of hypotenuses. So I'm really showing you this not to just show you where the formula comes from, but also to help you remember the formula, because you'll know, hey, I know it's a Pythagorean theorem thing. Okay, well, this next hypotenuse is the hypotenuse of a right triangle that's delta x2 by delta y2, and this hypotenuse is delta x3 by delta y3, and so on, okay? So that the arc length, which is the entire length, and they just call it arc length, okay? This arc length, which they call S, alrighty, S1, I'll call this guy S1. S1 is going to be the square root of delta x1 squared plus delta y1 squared. Are you okay that S1 is going to be equal to this radical due to the Pythagorean theorem? Thank you for nodding, Marsha, I appreciate it. And the same thing with S2. That next little hypotenuse is going to be the square root of delta x2 squared plus delta y2 squared. And S3 is going to be the square root of delta x3 squared plus delta y3 squared. Alrighty? And so now all I have to do is add up all these little s's, S1 plus S2 plus S3, etc., and I get an approximation of my length. And so I can do this. S is going to be the sum as I goes from 1 to n of the square root of delta x sub I squared plus delta y sub I squared. I'm just adding up all of my hypotenuses, okay? Well, you know what happens next. I'm not going to add up 6 or 7 hypotenuses. How many hypotenuses do you suppose I'm going to add? Anyone thinking infinity? Yeah, instead of having 6 or 7 partitions, I'm going to have an infinite number of partitions. So that instead of adding 6 or 7 hypotenuses, I'm going to add an infinity of hypotenuses. And you can tell now that no matter how curvy my graph is, if I'm adding an infinity of hypotenuses, those hypotenuses are going to hug that graph perfectly. And I'm going to get the true arc length of that curve, you know, by adding up an infinity of hypotenuses. So I'm going to let S be the limit as n approaches infinity, which, by the way, means that my delta x and my delta y are approaching 0, right? My little deltas are getting teenier and tinier. I'm going to get the limit as n approaches infinity of this sum, I equals 1 to n, of the square root of delta x sub I squared plus delta y sub I squared. Alrighty. And so now the next thing I'm going to do some algebraic trickery. I'm going to factor out delta x sub I squared. So this will be the limit as n approaches infinity of the sum as I goes from 1 to an n of the square root of delta x sub I squared times 1 plus delta y sub I squared over delta x sub I squared. Okay. I factored delta x sub I squared from both of these terms, leaving a 1 there and leaving that guy there. And now this square root of delta x sub I squared I can take out. So I end up with the limit as n approaches infinity of the sum as I goes from 1 to n of the square root of 1 plus delta y sub I over delta x sub I quantity squared times delta x sub I. And then here comes the weird thing. Do you remember what happens to my deltas when n goes to infinity? As my delta x's get smaller and smaller and smaller, what do the deltas magically turn into?
0.
Yeah, well, not 0, because then it would all be 0. But according to Leibniz notation, Leibniz doesn't use deltas. What does Leibniz use?
D.
Yeah, D. And so that's the weird magic. The weird magic is as n approaches infinity, as I get in an infinite number of hypotenuses or an infinite number of partitions, my delta x sub I magically turns into dx, and my delta y sub I magically turns into dy. And my summation magically turns into the integral symbol. That's how, many months ago we transitioned from Riemann sums to Leibniz notation of getting integrals. And so this ends up being the integral from a to b of the square root of 1 plus dy dx squared dx. And guess what? There it is. There's the Arclength formula. Now, most textbooks express it like this: the integral from a to b of the square root of 1 plus f prime of x squared dx. So you can think of it either way, f prime squared or dy dx squared. But regardless, there it is. That's the Arclength formula. All that's left for you now to do is mindlessly plug into it. So let's go for it. Example number 1. Find arc length of y equals x squared from x equals 0 to x equals 1. Good luck. I'll give you a hint. Please mindlessly plug into that formula. And you'll have to use your graphic calculator. Is there anyone not knowing what to do? You good? Okay. You looked quizzical. Okay. Your brow was knit. Okay, well, hey, here we go. F prime of x is equal to 2x, correct? So the arc length is going to be the integral from 0 to 1 of the square root of 1 plus 2x squared dx. That's simple. Well, what'd you guys get for that?
1.48.
Okay, good. I'm getting 1.48, 1.4789, so 1.48 is good enough. How many people got 1.48? Yeah, it's that simple. That's all there is to it, Now, one thing that's interesting is what would have been just this hypotenuse? What's the distance just from there to there, the straight line distance from 0, 0 to 1, 1? What's that going to be?
Rad.
What's that?
Rad 2.
Rad 2? Well, not. Is it rad 2?
This is a 45.
Yeah, 1.4. Yeah, what's rad 2? 1.414, right? So does that make sense? that guy would be 1.414, but the actual arc length would be longer. So I just wanted to see that it made sense to you guys. Yeah, thank you, it is RAT 2, 1.414. Okay, great. Well, you guys want to do another one? Should we do another one? Are you guys good on it? Here, let me see if I got another interesting one. No, I don't have any interesting ones. How about, oh heck, yeah. Okay, I'm not going to give you an interesting one. Here we go. Here. How about the get arc length of y equals rad x from 0 to 4. Try that out. Okay, this is a test to see how awesome your graphing calculator is. How many people here got an answer? Okay, how many people are still waiting for their calculator? Okay, good, so you guys have older calculators. It's not awesome, okay? Because look at this. Okay, f of x is equal to x to the 1/2 power, so f prime of x is equal to 1/2 x to the negative 1/2 power, which is the same as 1/2 rad x. Okay, so my arc length is going to be the integral from 0 to 4 of the square root of 1 plus 1/2 rad x quantity squared dx. And so I happily punch that into my graphing calculator, and my graphing calculator won't give me an answer. It just sits there and thinks for minute after minute. My calculator is still, oh no, it finally gave me an answer. Oh my God, my calculator gave me an answer. Okay, well, very good of you, calculator. I got 4.647. Is that what you guys got? Okay, great. Well, why did my calculator have so much difficulty doing this problem?
That's a lot. Is it because it goes through all of the Pythagorean theorems?
No. Yes, Abigail? Thank you. I'm trying to take an integral and plugging in a number that's undefined. You see that? My graphing calculator is trying to get an arc length, but when you plug in 0, you get undefined. You see what I mean? And so that gets us to our last thing. What if f prime is undefined within the bounds? Okay? Well, I gotta tell you, rather than hoping after 5 minutes my calculator magically gives me a right answer, what I need to do is go to dy land. Okay? And that's it. If f prime of x is undefined within the bounds of the integral, go to dy land. Okay? Let me show you what that entails. You know how arc length equals the integral from a to b of the square root of 1 plus f prime of x squared dx. You know how that's our arc length? I could also go to dy land. That is my arc. Instead of adding up all of my hypotenuses in dx land, going from A, let's say, to B, instead of going A to B, although that's kind of weird. Here, let's cut that a little bit. Let's make it like this. Okay. Instead of going from A to B, I can go from C to D. And I can add my hypotenuses from C to D, and then all my dy's and dx's switch places. And I'm not going to go through the derivation again. Just trust me, all the delta x's and delta y's switch places, so that you end up with this. You end up with the integral from C to D, because now your bounds are along the y-axis, and it's going to be the square root of 1 plus g prime of y squared dy. So all I'm asking you to do is to take your function, where is that? Take your function and just solve for x. And then get the derivative of that and stick it in there and have your bounds be from C to D. Let me show you how that works. Here, okay. This is the graph of y equals rad x, okay? Well, now I'm saying, hey, solve for x. Don't solve for y, solve for x. So I'm going to have y squared equals x, or 2y equals x prime. You see? Because this x is like, this is g of y. And so 2y is going to be g prime of y. I'm going a little fast, but is that okay? I'm going to solve for x and then take the derivative of both sides with respect to y. I'm going to get x prime, or g prime of y, because I'm getting an expression g of y. I'm getting a function in terms of y. And so this arc length is going to be the integral. Now I'm in dy land, so I got to do my bounds along the y-axis. So it'll be from 0 to 2. It'll be the square root of 1 plus g prime of y squared. So it'll be 2y squared, and then dy. And now I can plug that in my calculator, and I'll get an answer lickety-split. Here, math 9, square root of 1 plus 4. But of course, I'm still plugging in x's, because that's what my calculator is, so it's kind of weird. Okay? And you get an answer immediately, 4.647, just as it took my calculator forever to get. You guys okay with that? So I need to give you one more example like this. I need to give you another example where in dx land you're undefined, so you have to go to dy land, get the derivative with respect to y, and then mindlessly plug into the formula. So here comes the last problem we're going to do here. Second. Okay, here's example number 3, I guess. Get arc length of y equals x to the 1/3 power from x equals here, give that a try. And I hope you see, I'll just tell you right off, y prime is 1/3 x to the negative 2/3 power, right? Which is 1 over 3 times the cube root of x squared, which is undefined at 0. So you don't get to be in dx land here. You're going to have to go to dy land because you're undefined within the bounds. Your calculator will yell at you. So good luck with that. No, no, that would be it. Well, I got to tell you one more thing. I hope you notice I have a infinite, I have a vertical tangent there at 0. That's why it's undefined. My tangent's undefined at 0. So I had to go to dy land. And is everybody good? What would the bounds be? If I'm in dy land, what are my bounds going to have to be? Thank you very much, Kimberly. Yeah, -1 to 2. You guys okay with that? So this is it. This is how you deal with undefined. Now, we've got 60 seconds left, and there's one more scenario I got to make sure you're aware of. What if someone gives you, oh shoot, what if someone gives you a graph which is, where there's one non-differentiable point, like a corner point there, or someone defines a graph piecewise, then the last thing I want to tell you is sometimes you're better off just dividing up the graph. Just get 2 separate and distinct arc lengths. That's what's going to happen on tonight's homework on problem 28. You're going to get an absolute value, and you're just going to have to get the arc length from there to the corner point, and then the arc length from the corner point to the end. So be aware you can do it that way as well. Thanks a lot.